Hello, this is Deborah Chung at University at Buffalo. The subject is structural self-sensing, which means a structural material sensing itself without sensor incorporation. The concept is based on structure-property relationships, with the properties being the electrical properties. And this pertains to multifunctional structural materials, that is, the material serving structural and non-structural functions. There's no device incorporation, so low cost, high durability, and no mechanical property loss. Also design simplification and large functional volume. Having a device incorporated, that needs to be done during the fabrication of the structure, and repair might be difficult. Here we don't have any device, but the structure material is the sensor. So we measure the electrical properties of the structural material. Now here is a famous Miami building collapse. And it'd be nice if we know ahead of time that something's wrong. This is oil or gas wells, and cement is used as a sealant. If it's not good, then we can have an oil spill. So it's important to monitor the goodness of the cement sealing. The structural materials that I'll cover include the continuous fiber polymer matrix composites, as well as cement matrix composites. The attributes sensed include strain and stress, damage, and temperature. So electrical measurement is used for self-sensing. Measurements can be resistance, capacitance, or inductance. And I'll first talk about resistance measurement. Now, continuous carbon fibers are very attractive for their high modulus, high strength, and low density. They are widely used for lightweight structures, like airplane and cars, bicycles, golf clubs, tennis rackets, and so on. Back in 1993, I invented smart concrete, which is concrete or cement containing a little bit of short carbon fiber. And it's very important to disperse the fiber, and it turns out that the addition of silica fume, which is very fine particles, helps the fiber to loosen up during the mixing. And the smart concrete is useful for weighing trucks as they move, for the sensing need of autonomous vehicles, and for building intruder detection, weight-based kind of sensing without using camera, and also structural health monitoring to prevent hazards. Now, electrical measurement sounds easy, but there are a lot of pitfalls. First of all, let's consider the measuring of the resistance. There are two main methods, the 4-probe method and 2-probe method. Here you can see my holding a sample of cement, and it has 4 electrical contacts wound around the sample, and that's 4-probe method. The 4-probe method is better because the outer 2 probes are for current, the inner 2 probes are for voltage, and no current goes through the voltage probes. As a result, the measured resistance excludes the contact resistance. However, for the 2-probe method, the measured resistance includes the contact resistance. And in general, when you apply stress or heat, both the contact resistance and the specimen resistance may change. So you have two things changing, making it very confusing. Resistance-based sensing is often known as piezoresistivity, which refers to the change of the electrical resistivity due to strain. The severity of this effect is known as the gauge factor, which is the fractional change in resistance per unit strain. There are 3 styles of measuring the resistance: measuring the volume resistivity for sensing a volume, measuring the contact resistivity for sensing an interface, or surface resistance for sensing a surface region. First of all, volume resistivity. This is carbon fiber cement under repeated compression, having an arbitrary progression of different strain amplitudes shown by thin lines. And the thick line is the resistance, and whenever one compresses, the resistance goes down. And one can plot the resistivity and the strain amplitude and connect the data points in chronological order, and one finds that it's kind of linear with little hysteresis. This is done using the 4-probe method. However, if one uses the 2-probe method, this is how it looks. It's terrible. Now, how about tension as opposed to compression? Well, just the opposite. The resistance shown by bold line increases reversibly upon tension. But if you take away the carbon fiber, the effect would not be so good. The resistance still increases, but not very reversibly. Also, the extent of resistance increase is much, much less. Now, damage in concrete is a big headache. And freeze-thaw damage is very common in wintry places. And that is because ice has a lower density than water. So water expands upon freezing, and thus causing stress in the concrete. And we have succeeded in monitoring the freeze-thaw damage in real time by resistance measurement. In thin line is the temperature going from below 0 degrees centigrade to above 0. And the thick line is the resistance. And whenever the temperature rises, the resistance goes down. And this is because there are interfaces in the material, and a higher temperature would enhance the chance of electrons jumping across the interface, thereby decreasing the resistance. And note that the baseline resistivity increases steadily in every cycle, meaning that there's incremental freeze-thaw damage occurring in every cycle. At the very end of this life, the resistance shoots up, and that shooting up occurs at the coolest point of the last cycle. And this is mortar without carbon fiber. Now, another temperature measurement technique is thermocouples. And we can have cement-based thermocouples by having two dissimilar cement materials electrically connected. One is carbon fiber cement, which is P-type, that is positive thermal power. The other is steel fiber cement, which is N-type with negative thermal power. So we have the two in contact, making a p-n junction, and indeed, it gives us the Seebeck voltage reversibly and linearly with the temperature difference. Now, p-n junction is famous in the semiconductor world as a diode. Well, the cement-based p-n junction is not as beautiful a diode as the semiconductor p-n junction, but it has somewhat a diode characteristic, having more current flow in one direction than the other. Now, continuous fibers are more effective for reinforcing than short ones because the fiber matrix interface is never perfect. So let me turn to continuous carbon fiber epoxy matrix composite. Now, during the fabrication of the composite, the epoxy resin shrinks during the cooling. And as a result, after fabrication, one ends up having compressive residual stress in the carbon fiber. So if one takes a single carbon fiber and embed it in epoxy, and having the single fibers stick out at the two ends to accommodate A, B, C, D for the 4-probe resistance measurement, and then measure this resistance while subjecting the single fiber to tension. And one finds that the resistance decreases upon tension, and it's reversible. And that's simply because this tension cancels out the residual compressive stress. Extending from single fiber to composite laminate is the same concept. At the bottom shows the longitudinal volume resistance decreasing, okay, because of the same reason. And it's essentially reversible. Now, a continuous carbon fiber laminate with an insulating matrix, the through thickness resistivity is never infinity, even though the matrix is insulating. And that is because of fiber waviness, so that there's always fiber-fiber contact. When you have elastic longitudinal tension, that is horizontal tension, the fiber waviness would decrease, so the through thickness resistivity would increase. And this is exactly what we see for a laminate. At the bottom shows the through thickness volume resistance increasing every time one tensions it in the longitudinal or horizontal direction. Now, damage can occur in aircraft, say due to bird strike. And the damage mechanisms include delamination and fiber breakage. This is fatigue monitoring, tension fatigue with the tension in the fiber direction and the resistance in the same direction. And the bottom shows the longitudinal volume resistance decreasing in every cycle, as I mentioned before. But now for fatigue, I do many cycles. And for this 218,000 cycles, we see the first fiber breakage. Actually, the breakage involves a fraction of a toe, not a single fiber. And here later on, 299,000 cycles, we see the second spurt of fiber breakage. And toward the later stage of fatigue, we see a continuous rise in the resistance baseline in every cycle, meaning fiber breakage occurring at every cycle. And toward the very end, the resistance increases abruptly. So we see the entire fatigue life through resistance measurement. And the bottom shows the peak value of the resistance at every cycle versus the fatigue life. And you can see that the first spurt of increase occurs at about 50% of the fatigue life. The top curve shows the modulus. So indeed, the modulus decreases, supporting the fact that damage indeed occurs. Next, let's turn to contact resistivity, which is for sensing and interface. A composite laminate has various plies or laminae, and between them are interlaminar interfaces, which are the mechanical weak link. Any interface is associated with a contact resistance, and the interlaminar interface likewise. And this interface is a matrix-rich region, as you can see. And even though the matrix is not conductive, the contact resistivity of that interface is never infinity because of the fiber-fiber contact across that interlaminar interface. Now, delamination decreases the interlaminar fiber touching, thereby increasing the through-thickness interlaminar resistivity. And this is a modified four-probe method that I developed for measuring the contact resistivity of the interlaminar interface. So we have two laminae overlapping, and the junction is that interface. And we have four legs sticking out to accommodate the four contacts. And the contact resistivity is the contact resistance times the contact area. Another nice thing about this geometry of measurement is that we have a 2D array of sensors because we have a 2D array of interlaminar interfaces. And so we have 2D spatially resolved sensing. In addition, the XY grid of electrical connections are also built in to the composite. While this American Airlines flight fell down from the sky and landed in New York City, killing over 200 people, and the tail came off. And that indicates the fastening was a problem. Fastening involves squeezing or compression in the through thickness direction, which is the weak direction. So it'd be nice if we can monitor the compressive stress that still is there in the fastened joint. So we can measure the contact resistivity during cyclic compressive loading, squeezing. And every time we squeeze, the contact resistivity decreases because there's greater proximity between the two plies when you squeeze. However, for this epoxy matrix composite, the contact resistivity decrease is not totally reversible. But if you use a thermoplastic matrix instead of the epoxy matrix, it's totally reversible. The reason is that the thermoplastic matrix has linear polymer molecules, so it's more tough, whereas the thermoset, the epoxy, is brittle because of the cross-linking. So actually, it'd be better off if we use a thermoplastic matrix composite. Now, a composite panel is not very thick, So measuring the through-thickness resistance is not that convenient, but measuring the in-plane or longitudinal resistance is much more convenient. And we can do that. And we find that the longitudinal resistance decreases upon that through-thickness squeezing, just like the through-thickness resistance decreasing. And you can see the stress, and then the stress is the squeezing, and the through-thickness compressive stress here is decreasing. This is longitudinal resistance decreasing upon through-thickness compression. Okay, akin to the so the longitudinal resistance decrease is akin to the through-thickness resistance decrease under the same squeezing. Here's the reason. The through-thickness resistivity decreases due to the enhanced through-thickness fiber proximity, and thus promoting the longitudinal current path detour necessitated by fiber imperfection, and decreasing the longitudinal resistivity. That is, one is bound to have some imperfections in some fibers, and when that's encountered, the current needs to detour from one fiber to the next, and having more contacts between the fibers would facilitate that, thereby enhancing the in-plane conductivity. Now, damage often occurs in aircraft because of impact, whether by bird strike or by hail. So impact sensing is needed. And the interlaminar interface is a very good sensor of impact. Shown here is the contact resistivity of the interlaminar interface decreasing irreversibly every time one impacts. This is for increasing impact energy. And even at this tiny impact energy of 0.8 millijoule, we detect it. Now, the irreversible decrease in the contact resistivity of the interface upon impact is due to the irreversible increase in the fiber-fiber contact across the interlaminar interface. Now, this interface is also a thermistor. That is, the contact resistivity decreases with increasing temperature due to the chance of electrons jumping across that interface enhanced by heating. Not only is it a temperature measuring device, it's sensitive to thermal damage. This is the contact resistivity decreasing every time one raises the temperature. And at the highest temperature, there's a little bit of thermal damage, and that results in a little vertical spike. When the highest temperature is a little higher, then the vertical spike becomes more because there's more thermal damage. And here is even more. So we have temperature sensing and thermal damage sensing at the same time. Thirdly, I go to surface resistance measurement, which is for sensing a surface region. That uses electrical contacts that are on the same surface. So the current is injected from the surface, and it digs in only so much. It's incomplete penetration of the current. However, this is very handy when one wants to monitor flexural deformation. Because in flexure, one side is feeling tension and the other side is feeling compression. So we use 4 electrodes on each of the 2 opposite surfaces to measure the top surface resistance and the bottom surface resistance. And so here is the result. The compression side resistance goes down every time one flexes, while the tension side resistance goes up. Okay. The reason is this. Upon elastic flexure, the tension surface resistance increases due to the fiber waviness decrease. You're stretching, making the fibers a little straighter, consequently less current penetration. But the opposite occurs at the compression side. Now, carbon nanotube is very popular, fashionable, and people want to put carbon nanotube into almost anything. And here is cement in terms of the gauge factor, a description of how big is the piezoresistive effect. CF means carbon fiber, CNT means carbon nanotube, and you can see that adding the carbon nanotube to the carbon fiber doesn't help. It actually decreases the gauge factor. And the winners with the highest gauge factor are all those having only carbon fiber, not those with carbon nanotube. The carbon nanotube is not so great because of the intertwined morphology. So the dispersion becomes very difficult. On the other hand, if you want to modify a small place, such as the interlaminar interface, you need something small. So nanofillers would be good for that. And that results in a hybrid composite, which is called a hierarchical or multi-scale composite. However, such material modification has disadvantages because of the increased material and processing costs, and also the applicability to new structures and not to existing structures which would not have the required modification. Next, capacitance measurement. Conductivity relates to the resistance, but the permittivity relates to the capacitance. Conventional conductor has the electrons not interacting with the atom, so the electrons just loop around with no polarization occurring. But in this unusual situation, the electrons, a small fraction of them, interacts with the atoms, thus causing polarization in the conductor. So this is a conductive dielectric. It's a relatively new concept. So we measured the relative permittivity of graphite for various grain sizes, and we find that the permittivity increases a lot as the grain size is reduced. If one plot the permittivity versus the 1/, grain size, which relates to the grain boundary area per unit volume, the curve is more or less linear. This means the electron-atom interaction responsible for the permittivity occurs at the grain boundaries. Now, poling is not needed for the conductors because the polarized state is inherent, is natural due to that interaction. And no poling means no depoling. The capacitance-based sensing is applicable to all dielectric or polarizable materials, regardless of the resistivity, both conductors and non-conductors. Piezo permittivity refers to the effect of strain or stress on the permittivity, and I call the relative permittivity kappa. And shown here is the kappa increasing every time one increases the stress. Okay, higher the stress, the higher the permittivity. So this is capacitance-based stress self-sensing. And the bottom is the corresponding change in the resistance. The resistance also increases every time one tensions it. So both piezoresistivity and piezopermittivity occur in the same material under the same stress. And this is expected because the resistivity and permittivity are related through the Kramers-Kronig relationship. We can also use capacitance sensing for damage sensing, and this is a carbon fiber epoxy composite. We have artificial damage in the form of tiny holes along this vertical direction, and I have two electrodes, coplanar electrodes on the surface of this square laminate, and the current bows out from the two electrodes. The presence of the defects would make the bowing out not so easy because it intercepts the electric field lines. And so the presence of the defects would cause the capacitance to go down. And the perpendicular situation, which is here with the fiber direction being vertical, causes more fiber current spreading, and so it's more sensitive to the defects, and so the capacitance goes down more. Next, let's turn to inductance measurement. This is really new. I just started this research in March of this year. Twisting enhances the handleability of fiber tows or yarns. The twist level is known as the number of twists per inch of the tow, TPI, twist per inch. Twisted carbon fiber is used for weaving to make fabric. The twisting decreases the resistivity, because the number of fiber-fiber contact points is increased by the twisting. And because of that, the inductance is increased by the twisting. The fractional increase in the inductance is greater than the fractional decrease in the resistivity, meaning the inductance is a better sensing avenue than the resistance for the twisting. Now, how about both tension and twist? You see that this tension increases the inductance. So that's piezo inductance, and it's not totally reversible. And when you have more and more twists, the effect is more and more. The corresponding resistance change is similar. The resistivity increases upon tension, and with more twists, the effect is more and more. And also, the piezo resistivity is not completely reversible. So here I compare the twisting and tension in terms of the fractional changes in the inductance and resistivity. The resistivity decrease indicates increase in the number of fiber-fiber contact points. Okay? And twisting increases the number of contact points, thereby increasing the inductance and decreasing the resistivity. But tension decreases the number of contact points, thereby increasing the resistivity. And note that the tension effects are much smaller than the twisting effects. Here we compare tension versus tension plus twisting. The tension increased the resistivity regardless of twisting. And comparing the twisting versus twisting plus tension, we see that the twisting plus tension gives less inductance increase than the twisting alone. And let's compare the inductance values. Comparing 12K and 24K uncoated carbon fiber tows, you see that the larger tow has more inductance, and that's because it gives more fiber-fiber contact points. Comparing uncoated and nickel-coated fiber, you see that the nickel coating increases the inductance, and that's expected due to the magnetic character of the nickel coating. This last row is the 12K uncoated fiber with interlaminar interface between two perpendicular tows. And this last row gives by far the highest inductance. Now, this last row corresponds to this geometry. We have two tows, two lamina that are perpendicular, overlapping at this region, which is the interlaminar interface with epoxy infiltrated. And so you have the current path going from A to B, and the current path changes direction from A to B. And any change in current direction enhances the inductance, just like the change in direction of a coil as it coils around, Faraday's law. Okay? So there are three sources of inductance in composites: within the tows, the directional changes of the current path, and the interlaminar interface. There's fiber bending occurring within the interlaminar interface region, and that bending contributes to the inductance. So let's extend this to the composite laminate. And so here we have not just one interlaminar interface, we have a lot, because we have two laminae forming a composite. And you have the changes in current directions indicated by all these arrows. And so all these inductances are in series, and so it's additive in terms of the inductance. And this is just one current path. We can have numerous current paths in one two-laminar unit. And we can have a number of two-laminar units in a laminate. So potentially, one can build up the inductance to an appreciable value. And so I am dreaming to make this a structural electromagnet. This is a term that I coined. that is, it's an electromagnet, but it's not in the form of a coil, but in the form of just a two-laminar cross-ply composite. And it's a structural electromagnet because it's a structural material without modification, providing the capacity to be an electromagnet. There are some possible applications of structural electromagnets: motors, generators, transformers, lifting magnets, and magnetic actuators. That is self-actuation. That self-actuation would be in the through thickness direction, while the magnetic field would be in the in-plane direction. And all these applications need magnetic field. So my dream is to use the structural material to provide the magnetic field as needed for these applications. So this is beyond self-sensing. This is an unprecedentedly high level of smartness in structures. It's my dream, my future work. So here's the conclusion. Structural self-sensing involving resistance measurement has been studied for decades, but recent work has extended it from resistance measurement to capacitance or inductance measurement. Resistance or inductance measurement is applicable only to conductive materials, such as metals and carbon fiber composites. But capacitance measurement is broadly applicable to conductive and non-conductive materials, as long as they are polarizable. The effect of strain or damage on the resistivity or permittivity is the basis of the resistance-based or capacitance-based sensing. The effects of fiber-fiber contact, fiber bending, and current direction change on the inductance are the main basis of the inductance-based sensing.